Good morning, everyone from California. It's wet but beautiful out here. Good morning, Daniel.
Good morning, Nathan.
All right, well, we're looking forward to today's training where we're going to cover the coupling of batteries to solar systems. And the title of the talk here is Unlock a New Customer Base, Learn How to AC Couple Batteries to Existing Solar. This is a NABCEP certified course, AC and DC coupling. And the topic is titled down there at the bottom with a subtitle. Daniel, this is also so this is a NABCEP course. We would ask that everybody stays through to the end of the course to get their credits. This is also a topic that you and I are quite interested in because it covers solar panels and the kind of the details of how that solar is used. Before we get started on that, though, we often mention conferences that we go to. We were at InterSolar just a week ago, and that was an excellent conference. We enjoyed seeing a number of you there. You and I will both be running trainings at NABCEP as well, and that's coming up at the end of the month here in Reno, Nevada.
That's right. I'll be talking a little bit about codes and standards related to energy storage, specifically residential codes. So really excited. If anybody's going to be at NABCEP, please come by the booth. We'll have a special gift for you if you're here on this call. And Nathan, what are you going to talk about?
Yeah, I'll be talking about generator integration, Daniel. We also will be hosting Open Solar in our booths for some training sessions. Open Solar is a free design and proposal building software. It can do an excellent job at modeling the production that you would get out of solar systems. So please come by the booth. As Daniel said, we have some special gifts for you there. Sorry, here it looks like I clicked a link. So let me get back into our presentation.
As Nathan's pulling us back in, during this talk, we have disabled chat, but Q&A is open. So please go ahead and put any of your questions in the Q&A, and we'll address them as we go. Your comments, your questions really make this more of an interactive thing. Nathan mentioned at the end of this presentation, our email will pop up. Please email us your name, and we'll get those NABCEP credits over to you.
Yeah, and sorry about that. I do have the slideshow back up here. Daniel, we are going to be featuring the Solarc inverters a lot in this talk. That is our recommended inverter pairing. We have a partnership with Solarc. And one of the things that Daniel and I like about working together with Solarc is it's an American-based company based in Texas. And we have quite a good relationship between our teams, often offering joint trainings. We'll have a training coming up soon on advanced generator integration, so covering topics like how to use generators together with AC coupled solar, things like that, how to use time of use to engage when your generator is allowed to come on, things like this. So we are quite pleased with that partnership with Solarc. That being said, we are an inverter agnostic company, and our batteries can be paired with many different inverters that are on the market. And we have closed loop integration with other inverters as well. So stay tuned for some joint presentations with other companies coming up too. We also have put together these packages to help our dealers and installers share this content, share these options, share the variations that you can do with homeowners to make them understand. These packages are by no means set, right? We can always add batteries to solar systems by paralleling larger battery banks to smaller inverters, or adjusting the size. And one of the strengths of this offering is that you can scale the battery capacity, this storage, independently from the power needs of the home. These packages with Solarc also have the ability for us, both of us warranty our products for the off-grid market. You don't even need to you don't have to have an internet connection, in other words. You don't have to be grid tied as some of the competitors. We really have some versatile offerings together. So let's jump into the training. The scope of today's training is covering AC and DC coupling of solar to batteries. And so what we mean by that is how the solar, is connected to the battery. Now, there are also AC coupled batteries, and Daniel and I will discuss that briefly, but for the most part, we are talking about how the DC produced by the solar array gets into the batteries. So we'll be highlighting some of the battery backup options to existing AC systems. So there might be customers which already have AC solar, meaning kind of directly coupled, feeding back to the grid, so grid-tied systems, and want to add batteries. So we'll cover how to do that today. We'll also talk about best practices related to sizing AC batteries. So there are some sizing demands that are a little bit different for AC coupled systems, and how to use batteries to maximize solar production. So getting the most out of your solar system, getting the most financial benefit out of your system. So we often start here with the basics. And Daniel, I'll let you introduce this slide. What are we looking at here?
Of course, we're kind of looking at the basics of an energy storage system. In the context of this training, I think the key here is to understand that we DC couple a lot through the solar. It has its own built-in MPPTs, and we'll talk here in a minute exactly what an MPPT is. Solar produces DC. We feed that DC through the charge controllers, charge up the batteries. And then only when we need to use the DC to turn it into AC do we use that solar converter to power the home loads. I would also mention too that we see a lot of people adding batteries to existing solar systems. A lot of times those existing solar systems have microinverters or they may have string inverters. They are by design supposed to shut off with the loss of grid. Well, using energy stored in that battery, we can then create a grid form, right? The solar can be a grid forming inverter, and it will create that grid, tricking the Enphase or the Solar Edge or whatever string inverter you might have to continue running, and then using frequency shifting, which Nathan will talk about here in a minute. One thing before we do go on, I know a lot of people on this call might be in states that have got rid of their net metering. You can add energy storage to existing solar systems and remain on those favorable net metering agreements. So that's really key to understand. Additionally, you can add energy storage to an existing system and still leverage the 30% IRA ITC tax credit in addition to the labor, the materials that might go into doing these systems.
Yeah, and it is important to keep in mind that, as Daniel said, the benefits of leveraging that IRA, that comes just with adding the storage, right? Even if there's existing solar, you still qualify, and it's everything, right? It's the full cost of the system, the labor, the materials, the batteries, right? You can claim the tax credits for that. Now, we don't want to be misquoted. We are not saying that you can add a generator to existing solar systems and claim the renewable energy credit for that. Right, so do want to be clear that generators do not qualify, but batteries do. Daniel, you mentioned here, and while we're on this slide, we're about to skip here, but you mentioned the benefit of, or you at least mentioned coupling solar panels directly to the batteries without inverting, without converting that electricity to AC. Why might we want to do that? Why would it be beneficial to do that?
Well, one of them, it's more efficient to not have to switch between DC to AC, AC to DC. Another one can be inverter clipping. Now, when I would sell a solar, I would usually, I was some power dealer for a long time. But what we would do is we would have a Maxion panel, maybe a 400-watt panel, but yet that IQ7 microinverter, or the IQ7 Plus microinverter might only be able to do 320 or maybe 340 watts, which is acceptable to have some inverter clipping. Most of the time in the morning, in the afternoon, the panel isn't producing all of the 400 watts. But by using our DC coupling charge controllers, we're able to kind of eke out a little bit more of that power during the midday times when that panel is producing. Again,
Thank you, Daniel.
there is acceptable.
Yeah, you mentioned two topics there. One, the energy loss when you do invert, right? So when you convert the electricity from the DC that the solar panel produces to AC, you lose some energy, right? And that is the production of heat inside the inverter, right? And then converting back to DC to charge the battery again, there's another conversion process, AC back to DC. And so there's losses in both of those systems. And so typically DC coupled systems are somewhere around 10% more efficient. You're looking at around 95% efficiency on battery charging from solar when you're doing it with a DC coupled system. Now, there are plenty of variations in that. So I have to say, like 95% plus or minus, right? But then with an AC coupled system, you're looking at more like around 85 to 90% efficiency. So you lose a little bit of energy there. We're showing some microinverters. We're going to get into it a little bit here. And so let's keep moving through the slides here, Daniel, but I think let's keep that in mind as we talk about how to couple the systems. So when we're talking about coupling of batteries, we are talking about batteries that are DC batteries. We're talking about how the solar is coupled, right? So when we're saying AC coupled solar, what we mean is that AC power is coming from the inverted solar array and then being converted into DC power by a battery charger. So for example, Daniel mentioned having a solar edge inverter on your system, which is a grid-tied system. You want to add a battery. Well, that solar edge inverter is already permitted, it's already in place, it's already connected, it's already running, right? But if you want to add a battery system, what we could do is bring in a solar converter, bring that power as AC power from that solar edge into the solar, convert that AC power into DC to charge the batteries. That's what we mean by AC coupling in this context. We're talking about how the power from the existing solar is brought to the batteries. DC coupling, what do we mean by that, Daniel? We've got DC produced by a solar array, and we're sending that through MPPTs, right? And keeping it as DC, just maximizing the power production. Generally, this is done with MPPTs. PWM controllers are becoming less and less common in all but the smallest of systems, right? You can get a PWM pulse width modulated charge controller very cheaply, but almost every residential size system and larger is going to be using MPPTs. And then there's also, I do want to mention it here, there are also AC coupled batteries. What are those, Daniel? What's an AC battery?
Well, essentially, I mean, all batteries are DC. It's just that the inverter and charger are built into the battery case itself so that you have multiple batteries. And you had mentioned, Nathan, that you can't decouple the inverter charger for the battery if it's all built into one, where if we separate those out, we can scale energy and power separately. Nathan, I did want to make one point. You know, on specifically Enphase, everybody kind of liked the Enphase microinverters. I know I did, and I kind of still do. The idea is that you get module level monitoring. They have optimization or the ability to not be impacted by shading. And also to be able to kind of string together the AC conductors and just bring AC off of the roof. Well, now that the requirement for rapid shutdown has come into play, we're already going to have module level electronics up there anyway in the form of rapid shutdown, maybe even optimization with Tigo, and they do offer that module level monitoring. So even though we're not using microinverters, we can still leverage a lot of the advantages while still being better by having that non AC to DC conversion losses.
Yeah, you get it overall. There are advantages to both, right? You mentioned how AC coupled solar arrays can do a little bit better with shading issues, and we're going to jump into that. But having a DC coupled system in full sun, you're going to be more energy efficient overall because you're not doing as much of the conversion process. Every time you take electricity and switch it from one type to another, inevitably you're going to generate some amount of heat, right? And that the heat that comes from that conversion process, that's your energy loss. So here we're showing an example of a solar cell. We mentioned batteries and solars as innately being DC systems. You can think of a solar panel, and this is a topic that I've studied in depth in college. This is what I did a dissertation on 20 years ago. But this is the conversion of sunlight into electricity in a solar module. And it happens at the cell level on solar panels. And what you have is a transparent layer on the top, and you have effectively have what's called a PN junction. And you can think of the solar cell as a little bit of an electron pump. So when the electricity comes in, it excites electrons, and there's a built-in electric field which kind of pumps the electrons down in the solar cell, creating a deficiency on the top of the cell, the positive side of the cell, and creating an electron-rich section on the bottom side of the cell. And so if you look at the solar cells themselves, they have these collecting nickel strips on top of them to carry the electricity that's generated, and each cell kicks out about 0.62 volts, right? It depends a little bit on temperature, but it goes up and down with the use of the solar panel. So I'll explain that here in a second. But in order to get a higher
Nathan,
voltage panel, go ahead, Daniel.
I was going to say, Nathan, I think we need to update this. At Intersolar, I noticed almost every module that I saw on display was a bifacial one. So if anybody here on this talk has started to do bifacial, please put it in the chat and tell us what you think.
Yeah, bifacial
Or the
panels can give
Q&A.
you a gain as well, right? It's become so cheap because of the mass manufacture of solar panels. Solar panels have become so cheap, they're almost the cost of windows now, right? And so it is not an excessively expensive thing to add solar absorption on the backside of the panel. So what Daniel's talking about with bifacial panels, you can have solar production from the backside of the cells in addition to the front side. Um, Additionally, we're also seeing a lot more split panels, Daniel, split cell, where we've got essentially the top half of the panel and independently producing electricity from the bottom, and those two paralleled. So that can help in shading issues as well. I mentioned that the bifacial panels are not very beneficial if you're doing a roof mount array, right? You don't have much light on the backside of your panel, but for ground mount arrays, you can get 15 to 20% solar gains depending on, what the background is. With grass, I think it's 10 to 15%, additional power generated from a solar panel because of that reflected light that can come to the backside of the panel. So for ground mount arrays, that's important. So when you produce this DC electricity with a solar panel, you put a bunch of cells in series with that module to up the voltage, and then you put a number of modules in parallel or series, right? Often it's strings of cells that are in series with a DC system to get your voltage up to higher voltages. Higher voltages, less amount of current overall, are more efficient ways to run electricity. And so if you're running a solar array a long distance from your charge controller, highly encourage you to use the upper voltage range of the MPPTs. What happens in a solar panel, though, is the production of electricity, and it's like I said, you can think of it almost as a little electron pump. If we pull all of the current off of that panel, we are essentially short-circuiting the panel, and that is the maximum amount of current you could get out of the panel, but your voltage is down. Daniel, what's power? We're a DC system. How do we compute power?
Oh, VI, right?
Right?
Volts times the
Exactly.
amp equals watts. Ohm's law.
Yep. It's, well, not Ohm's law, not necessarily Ohm's law,
Oh,
right? But power production is voltage times current, right? And so what we want to do is maximize the power production of a panel. So if we draw a little less than the maximum amount of electrons produced, we'll still have a voltage. And the voltage is essentially the difference in electron density between the top of the panel and the bottom of the panel, right? And so we want to keep voltage high, but we also want current to be high. And so if we vary how much current we're pulling off the panel, it balances out that kind of voltage, which is coming from the electron density difference, with the current. And so an MPPT does exactly that. It varies the amount of current being drawn off of a panel to maximize the current times voltage, which is power out of a panel. And so an MPPT is doing that. For a DC coupled system, we're maximizing power production of a panel. I'm not going to go through this slide in detail, but essentially you should know that when you take solar panels and you string them together in series, the voltage goes up. The current would be limited by the lowest producing panel, but essentially that's current stays the same, voltage goes up when you series panels. When you put panels together in parallel, the voltage is essentially the same across all of those panels, but the current adds. So typically we're looking at one or two panels in parallel, and then pairs or singles of those panels going together in series. Often we're looking at just a single string of maybe one panel by 9 in series, right? And that'll jump your voltage up to 400 or 500 volts. We're looking at a panel here, which, Daniel, what's the difference between operating voltage and open circuit voltage? Why does a panel, a 50-volt panel like is shown on the screen, not give us 50 volts when we're running it?
Temperature and also the PowerPoint of where we're going to be drawing down.
Yeah.
You know,
Yeah.
one thing I wanted to mention, Nathan, is on the previous screen, we had shown the maximum power point of the voltage at 18 volts. So this must be like a 36 cell module, which for me back in the day using old PWM charge controllers was pretty close to where we needed to be able to charge a 12-volt battery bank. And then on the next slide, Nathan, this panel, right, has a much higher voltage, which is be more acceptable when we're using a charge controller with maximum power point where it can adjust that point to meet what we need to charge at the batteries.
Yes, good point. And Daniel, we just talked a little bit about, what can influence the voltage of a panel. Certainly the amount of current that comes off of a panel changes the voltage. That's what this slide is showing, right? But you also mentioned about temperature. So, when you are sizing your solar array to fit with your charge controllers, and your charge controllers have an upper temperature or upper voltage limit, like for instance, on the Solarx, it's 550 volts DC. We have to account for cold temperature conditions. So under cold temperatures, voltage of a panel goes up, right? And so temperature has a big effect on the voltage of a panel, and then sunlight has a big effect on the current of a panel. So if you're looking at the output of a solar array, current goes up with incident sunlight, right? So the amount of sun it's capturing, and then voltage goes up with decreasing temperature. Okay, well, we could convert that power output of each individual panel directly into AC, right? And what we're looking at here on this roof is a series of, I think those are IQ8s, maybe IQ8 pluses, on solar rails, right? And the panels are about to be placed on top of these rails and connected to each one of those microinverters. So those microinverters are going to change the electricity output of the individual panels directly into 240 volts AC, and then we will parallel each of those panels up. So there are some advantages in that. If I go back a previous slide, you'll notice there's some shading on that panel that's closest to us in the picture. Well, if we have a string of panels in DC, right, that shading can affect all of the panels farther down the string because the current will be limited to the amount of current produced by that panel, which can be significantly reduced with shading if there's not a DC optimizer, right? If we don't have a way to bypass that particular panel. So there are a couple of ways to avoid that for DC. We've got split cell panels where the top and the bottom are in parallel with each other, and we don't get as much of an effect from DC. But we also have DC optimizers, which can bypass that panel as well. Okay, so here's an example of an AC system. We're looking at optimizers here, DC optimizers on a roof as well. And that looks like that's going into a solar edge inverter. And then these are examples of AC coupled systems. What are we looking at here, Daniel?
Charge controllers, some of the
Okay,
classics.
yep. So yeah, the Midnight Classics are there. That's a DC charge controller that many of us have probably installed. There's a little PWM controller up there on the top as well. Those units go for about $10. And then there's the Victron system. Those Victron smart charge controllers are commonly used, especially in mobile applications. So a number of different examples. Typically, charge controllers are current limited, and they have a range of voltages that are acceptable. I think with the Midnight Classic 100s that are out now, you can do 100 volts of incoming solar. It might be up to 150 with those. They are also, but they're typically current limited, right? So you can have a certain amount of current that comes out, and then the power out of one of those devices, you get more power when you go to higher voltages. A PWM charge controller produces a voltage by modulating the amount of time, essentially by getting an average of the voltage. So what it does is very rapidly, in the order of milliseconds, turns on and off DC power to approximate a voltage. And so by doing that, you can create a voltage which is reduced to kind of match the charging needs of your battery by pulsing on and off the supply coming from a solar panel. So we're showing an example of pulse width modulation there. The MPPTs that are currently built into many of these hybrid inverters, like the Solarcs, those are maximum power point tracking devices. And as we mentioned earlier, what you're doing with the MPPT is you're turning your varying amount of voltage, or sorry, you're varying the amount of current that you are using to charge the batteries. And by varying it up and down, you'll see an increase of the voltage or a decrease in the voltage when you vary the current. By doing that, the MPPT is constantly monitoring the product of current and voltage. And so if it steps the current up a little bit and the voltage drops down too much, you get off the end of the knee here and you're producing less power. And so that would then go the other direction. And so it's constantly going back and forth around this maximum power point to maximize the power output of the solar panel. Daniel, what is this?
What we're looking at is a couple of our PHI batteries. So we definitely have a really great new product. It's our 6.6 stacking battery. That's a 48-volt stack. We're still offering what we'll call our legacy batteries. In this example, we have some PHI batteries down there at the bottom, all going to a DC bus, basically a big metal bar. And then that's then feeding separately into the charge controller and feeding separately into the inverter. So unlike a lot of the hybrid inverters like the Solarc or the Solis, these components are still separated out into their individual parts and pieces.
I'd say that Victron is probably the king of modular systems, right? They have independent components for shunts, monitoring current. This is a smart solar charge controller. And so what you see is solar power coming into that charge controller. It uses MPPT, and it is an MPPT that'll do 75 amps here that is going to be charging these batteries with DC. And then that's outputting that DC power directly to the inverter to power loads or to interface with the grid. Similarly, it could bring grid power into the inverter and charge those batteries with DC as well. So it's a very simple example of a DC coupled system.
One other thing on that charge controller there, Nathan, is also has a load output. It has the ability to have DC coupled loads. I thought would be kind of an interesting thing, and it can then turn off those loads just like that Morningstar could when the batteries reach a certain percent state of charge or certain voltage. It can cut off DC coupled loads.
Mm-hmm. And here we're looking at another system. It's a DC coupled rooftop system. We've got a DC array coming through a disconnect there. That solar array feeds into the Solarc inverter, which has built-in MPPTs. I think that's a Solarc 15K, so it's got 3 independent MPPTs. You could have 3 different strings of solar coming in there. And then we've got that DC coupled to a battery system. And this system is also featuring one of our Briggs Stratton inverter or generators, which can be started up by the inverter. So the inverter has the ability to control starting and stopping the generator if it's needed, right? So if solar is not substantial enough, grid is down, the batteries are draining, the inverter can automatically, with our 2-wire signal to start up that generator, feed power back to the inverter and charge the batteries and cover loads. So we're looking at here a system that is coupled to the grid. So we've got a grid input here, and then we have a load output here.
Nathan, I want to mention there's a reason we have 40 amp breaker feeding to that main service panel. With the 120% rule, right? That's a 200 amp breaker, 200 amp main. That means we can 40 amp feeder. But you notice we have 50 amps coming up to our critical loads panel. What I've seen in the market is really exciting is these PCS control or CRD, where now we can program the Solarc to never sell back more than 40 amps, but yet we can land a larger breaker on there to support those critical loads. That is going to avoid us from having to do a main panel upgrade or perhaps having to derate the main. So I know this isn't the topic in today's talk, but I just wanted to mention that.
Yeah, the 120% rule, I appreciate you mentioning that. And I do believe maybe this is supposed to be a Solarc 8K at 50 amps of output. You can get actually 60 amps with that 12K as well, the pass-through that's there. Daniel, SolarEdge and Enphase years ago, so this is a little bit old, right, had a huge percent of the market. And the reason I have this slide in here is, it was Enphase, SolarEdge were owning 95% of the global inverter market. This has probably changed over time, but the reason I put this in here is to remind us that with net metering agreements that were very popular throughout the world, the majority of systems were just AC coupled. And what we were using the grid essentially as the battery. What's changed in California? I know you've done trainings and talks about what happened in California last year. What is that?
Yeah, the net metering, the idea that you can no longer just sell back to the grid throughout the entire day, throughout the entire summer, and then use up those credits during the night, during the winter on an annual true-up basis. Now that we have a net billing tariff, really we have to now use the solar during the day to charge up a battery and then discharge the battery at night to loads. And Nathan, I do think there are some other inroads. I know AP Systems is coming out with microinverters. And at the Intersolar show, if anybody was there, please put it in the Q&A. I do see other people coming to market with micros.
Yeah, good point, Daniel. Speaking of micros, what are we looking to hear?
So an IQ, I believe those are IQ7 pluses. It's hard for me to tell. And then what we're doing is bringing that into the Enphase combiner. That disconnect and combiner can be combined all into that IQ3 combiner there. It does have some of the disconnects in there per some of your local AHJ inspectors. It also has the ability to bring in multiple strings as well.
Yeah, and so this is a classic example of an AC coupled system, right? Your power can feed into your main panel. It's quite a simple design, right? There's no batteries here. There's no backup. If the grid goes down, your solar's off, right? And that's one of the disadvantages to an AC coupled, or sorry, an AC system like this, a grid tied system, is when the grid goes down, you don't have backup. And so there are ways to utilize that micro array when it's on the roof, right? So where those microinverters can be kept on even when the grid is down. So what is this?
This is, I believe that's still a Solar 5K. Again, we're now showing the 60 amp going to that main panel. And then we have those same Enphase microinverters coming into that IQ combiner. But in this example, we're going to land it on the Gen port inside of that Solar.
Yep, and so we've got AC solar comes on. So now if grid goes down, I think this is labeled as an 8K here, but when grid goes down, right, instead of the solar turning off, this inverter can do what you mentioned earlier, Daniel, grid form, take the power from the batteries, create a grid that's isolated from the main grid, right, to create a microgrid. And so we have AC power available now to keep the microinverters on, and they do what's called grid following. And so they're going to follow the microgrid that the solar creates and keep power coming both from the solar and from the battery to feed loads. If there's excess solar power, those batteries can charge up from that AC coupled solar array. And so we've got backup power now by adding the solar converter to this system. We'd call this a retrofit, right? You had an existing AC, you had an existing grid-tied system, and now you wanted a battery, so we've AC coupled this existing solar through a solar. So grid goes down, that inverter uses the batteries to create a microgrid, and those microinverters supply power to it. So we keep that solar active. What are we looking at here, Daniel?
A Solar 15K. So very similar to the 8K, but this one has the ability to do a 200 amp pass through. So in that previous example, we showed non-backed up loads and backed up loads. Now we're just bringing that meter right down to a service disconnect right into that Solar 15K with the 200 amp pass through, right back out over to the main panel. You do notice that we not only have the AC coupled solar on the right, but we additionally are able to add DC coupled solar. We can bring in both. So perhaps the system that was out there, they got some old AC coupled panels on the roof. They're adding an EV. They're adding heat pumps. We can then add additional solar and bring it in through that DC charge controllers as well. We're also looking at the rapid shutdown button, which is going to be key Normally, these AC coupled systems are just looking for the presence of grid. And if they see the loss of grid, they're going to shut themselves off so we're not backfeeding the grid. With these grid forming hybrid inverters, they're essentially creating a grid for the not only the grid tied solar, but also being able to bring in that DC and sending up the keep alive signal. So by code, we need to have that rapid shutdown button for the first responders. They can hit that and it will then, in essence, stop the grid forming abilities, which will then in turn shut down those microinverters.
Yeah, and the rapid shutdown buttons on the Solarcs, it's a normally open circuit. When you do press that button, it shuts everything off. It shuts the keep alive signal off to the rapid shutdown modules, as Daniel mentioned. It shuts the loads off to the house and shuts the AC coupled panel down as well. What that does is it makes everything safe, right? So if there is a fire, if there is an emergency, that means that the panels are all shut off at the panel level, which is required by that rapid shutdown requirement. So Daniel, taking a quick look here at what a 15K looks like. This is just another wiring diagram where we've got AC solar coming from an inverter going into a Solarc 15K with batteries. No DC coupled solar is shown in this example. So this is battery backup when you have an existing AC coupled solar. And that comes in, as you mentioned in the last slide, through the Solarc's generator port. So here that is in more detail. We're showing this with from the Solarc 15K manual, and you can see here that solar is coming in. You've got the junction box combining those micro inverters, allowing for a shutdown as well, and that's where you're getting your monitoring from an end-phase system. That is coming, L1 and L2 are coming directly into the generator port on a Solarc. You could also add, as mentioned on the left side of this screen here, you can add DC solar still through the MPPT. So you can have both. They're not mutually exclusive.
One comment, Nathan, is that you can, and there might be opportunities to actually land those AC coupled inverters into the load panel. You're going to lose the ability to monitor the solar production through the Solarc app. It'll still work in the Enphase app, because some of those loads may be consuming that. That is an option that then frees up that gen port to be used as a smart load output. So there's a couple ways you can do that. Just for this example, though, we're showing it coming in on the gen port.
So here's a look at inside that Solarc. So this is a 15K. We're looking at it on the left side. You can see the battery. We were mentioning the battery inputs. And then here was the DC coupled solar inputs. And then here is the generator where that AC coupled solar would come through. You've got your neutral and your grounding bars underneath. And then this is your load output. As Daniel mentioned, this is rated for 200 amps. So up to 4-aught aluminum could go in there, or 3-aught copper. And then we've got our grid coming in on this side. So these are rated at 200 amps. The generator port is rated at 80 amps continuous. On the communication side, we are highlighting here, these are where CTs would go, 3, 4, 5, and 6. And then that the e-stop button that Daniel and I were mentioning earlier would connect on the terminals labeled BB there. We are looking at the wiring of a Solarc 15K here to one of our 6.6 battery stacks. That's the newer battery that you can see on the screen there. There's also the option to include an energy track gateway. So that's the Briggs Stratton gateway that can monitor your batteries. So if you had 6 batteries in a system, it can monitor all of those individually, get you information about each of the individual batteries. We are showing here an example of how to wire this system when you have multiple batteries. So here in this case, we've got 9 battery modules, and we're showing how to do the communications here. So going from one battery to the next, one battery to the next, that's called daisy chaining. And so our batteries are connected, allowing communications between each of the individual computers inside the battery modules, the battery management system. And that allows the controllers to aggregate that battery information, pass that through the dongle here into the Solarc comms port. Once we hook up our battery systems with a solar. So we're showing an example here for one of our training walls. We do need to set the solar up to be able to communicate with the batteries. And this button here, the BMS lithium battery, we need to have that box checked in order for our batteries to properly communicate. If that box is not checked, the solar is not sending out appropriate signals on the CAN bus channel, and the batteries might not even produce an output because they're protecting, because it seems like something's wrong. So when you're first setting up your solar, you do want to make sure that you go in. By default, this is unchecked. You want to go in, check that box, click OK, then connect your batteries, then power on your batteries to the system. So if you have a grid-tied system, you can do that by powering on with the utility. If you're off grid, you might be able to power on with a generator, or if you're just have a battery in a solar system and you're off grid with no generator, you can power on with the batteries. Just don't connect the communications until you get that BMS box checked. So here we're showing programming the batteries. So this is for a single stack of batteries. We're showing the values to program in for the right charging and discharging rates. The battery capacity will automatically come in once you have the communications properly set up. And then the max charge and discharge rates here are global values. What I mean by a global charge and discharge rate means solar combined with any other type of charging source. So it could be solar plus grid or solar plus a generator. So the DC and the AC charging combined. In the next tab, we have the ability to specify how much charging we want to come from the AC sources. So if we're using the generator port to charge, as you would be doing with an AC coupled system, like an Enphase or a SolarEdge AC inverter, you can limit through whatever's coming through that gen port to charge at whatever rate you want. So we're looking at here, this is 60 amps. And Daniel, AC or DC?
Now that's in DC, so that might be 3,500 watts perhaps?
Yeah, it's about 50 volts. Typically charging occurs between 50 and 56 volts for our batteries, right? So if you're looking at 50 volts at 60 amps of DC current, that amount of power would be about 3,000 watts coming from the AC coupled solar. And then on the grid side of things, when grid is available, we are allowing the battery to charge from grid at 100 amps. The battery discharge menu controls how quickly we allow the inverter to power from the batteries, and it also has these set points. The set point of 50% here is if the system has shut down due to a low battery and the grid being down. We have to come up to that value in order to turn load support back on. Low battery is exactly that. It gives you a warning when you hit this value, 20%. And the shutdown voltage is the voltage or the percentage at which the inverter turns load support off to preserve the battery, right? So these are adjustable values. The battery empty voltage tells the inverter where 0% state of charge is for the battery system. You will also note here that the voltage column is grayed out. That's because in the previous battery tab setup, we had chosen use percentage for programming. And if you have one of our communicating batteries, they automatically choose percentage. So for an AC coupled system, we can program in for those microinverters and that charging into that battery setup menu. That occurs under the Smart Load tab. So once we go into a solar, we can go into the battery setup, and then we'll go to the Smart Load tab, and we need to let the inverter know, hey, we've got AC coupled on the input, on the generator input port. So we check this box. If we have a feedback agreement with the utility, which you're probably going to have if you have AC coupled solar, then you want to have this box checked for on-grid always on. We do not want the AC coupled solar to be on in some circumstances, Daniel. If the grid is down and the batteries are full and there aren't enough loads to consume that AC coupled solar, what do we want to happen?
Well, we want the AC coupled solar to shut off, and usually we have it shut off around 90%, right? Battery state of charge. So we're not kind of at that upper limit. It does take a little bit of time, probably not as much time as I think, to be able to curtail some of that AC production by adjusting the frequency of the grid that we're forming inside the hybrid inverter to trick those microinverters into shutting themselves off.
Yeah, it's important to keep in mind that AC coupled solar pushes out as much power as it can. That's its job. And traditionally it's been used to push as much power as it can back to the grid. But if the grid is down and the microinverters still see a grid through the microgrid that the solar is kicking out, right? The AC coupled solar is going to push as much power as it can into the solar. And if we don't have loads on in the house, that power has to go into the batteries. And if the batteries are full, well, that could damage the batteries. And so what happens is we keep those microinverters alive as long as something is consuming that power, whether it's battery charging or loads. But if the batteries get full, we shut off that solar. There's nowhere for it to go. We let the system run off of batteries for a while. And then when we get below 80% state of charge on the batteries, we'll turn that AC coupled solar back on. So that's what's happening here. We can also do some things like control the power output through the limiter option on the Solarc. So this allows us to use time of use and control how much power we are allowing through the different sources. So we could change the charge rate or change whether or not charging is on from the AC coupled solar with this. I'm going to skip ahead here. We've got a number of slides left. A quick time check for us. We've got about 15 minutes left. Daniel, in some cases, we're going to want to have a generator as well, right? And here's showing an example where, a typical example where we've got a generator already connected through a transfer switch on a home. Maybe this homeowner has come in and decided, hey, I want to add some solar to my system. We keep that transfer switch, we keep the generator back up there. And so either the grid or the generator is coming in through the utility port, the grid port on the generator. And so that's what's being shown here, but you can see they've got batteries added to their inverter and they've got solar added to their inverter. So we're going to choose priority. What do we want to back our house up with, right? Well, solar power is free, right? We're not paying for the sunlight, right? So as long as there's solar and battery power, we're going to back up the house off the batteries first, the solar first. But if those batteries drain down, the inverter can send a two-wire signal to start. It can start up the generator. If the generator is started, it would cause that switch to move over, the transfer switch to move over to the generator. And that allows power from the generator to come in, feed the loads, and charge those batteries up. So this is a kind of a dual backup system. You've got the generator there in case the solar is not producing enough power for backup, and you've got the solar and batteries there to give you the initial backup.
There's a couple reasons
go ahead.
to bring in that generator on the grid port. One is that you can leave that existing transfer switch there. Two, you can bring in a much more powerful generator onto that grid port than you could on the gen. I guess the last one would be by doing the generator in on the grid port, you free up that gen port to be able to use as a smart load output, or in this example, to bring in AC coupled solar. And Nathan, I know you're going to get at it, is we talked earlier about the Solarc being a grid forming inverter, but when the Solarc is connected to the grid, it's a grid following.
Sorry,
and
generator.
Yeah, or the generator. And as soon as it sees an AC coupled source, it's going to start following that. That's fine for the grid with AC coupled solar because we can backfeed to the grid. But when we have a generator, we don't want to backfeed. So what do we have to do, Nathan, if we're going to have AC coupled solar and a generator?
Yeah, so there are a number of different things you can do. So, Solarc advises, hey, program your generator not to run during the sunlight hours. So that's one way to do it. With Briggs and Stratton systems, we've got another way to do this. So if you're using one of our Symphony choice transfer switches, what you can do is you can use a lockout module, so a line voltage lockout module. So anytime that generator is running, we can disconnect that AC coupled solar so it doesn't backfeed the generator. Another way to do this, if you don't have a Briggs & Stratton transfer switch, is to use a programmable lockout module. It's a line sense module. And I think, Daniel, you've got a product there on the left side of the screen, one of those PSP lockout modules. I think those come in 60, 100, and even 200 amp varieties. So those are programmable as well. So they could do a similar thing that we're showing on the screen here.
But Nathan, if the AC coupled solar is producing power, the generator shouldn't come on though.
Well, there are cases where cloud cover, right, can mean that the AC coupled solar is weak, right? And so you're still draining your batteries. And so if your batteries get drained below that set point because of weak solar from the end of the day, for instance, yet heavy loads on the house, or weak solar because it's early in the morning and the batteries are still dropping, you come in, you turn on that microwave, you turn on the toaster in the morning, the solar is there, but it's not strong. Well, those batteries can still be dropping and trigger the generator to start up. So it's rare, but we certainly want to make sure that we protect that generator from backfeeding. And these line lockout modules, I think that programmable one that you're showing on the left in a 100 amp version is something like $150, $180. And the line modules that you're showing on the screen are about $100 for the Symphony 2 line voltage lockout module. So certainly worth it to protect that generator. So yes, it's rare, but there are times when we can have AC coupled solar on at the same time as the generator unless we are careful about blocking it. Daniel, what are we looking at here?
We're looking at the pinouts for accessories inside of a Solarc, and we're kind of calling out pins 7 and 8, which will be used for the 2-wire signal to start. Thankfully, our generators from Briggs Stratton can be started using 2-wire signal to start, normally open. So when the call for the generator comes, it's going to close that dry contact and start up the generators, either our vertical or our horizontal ones, and that's pin out 4 and 5 on our generators.
Yeah, and I think that one of the strengths of the Briggs & Stratton offerings is that we offer transfer switches, we offer generators, we offer batteries, right? And our generators, our batteries pair very well with the Solarcs. It's very easy to add a generator when you've got Briggs & Stratton batteries and a Solarc inverter. What are we showing here, Daniel?
We're talking a little bit about if we are going to have a generator on that grid port, a little bit of the settings that we need to do in the Solarc. In the middle, we're talking a little bit about some of the settings we're going to have to do in the generator so that even though the generator still may see the presence of grid because we're using the microgrid to power up the charging of the starting battery, maybe warming kits inside the generator to still start up if it sees 2-wire signal to start. And then on the far right, what we're talking about there is, you mentioned it earlier, is the charging of the batteries from the grid port, whether it be a generator, whether it be the grid.
Yes, excellent. Thank you. Daniel, I'm showing here the 6.6 battery. This is the newest battery from Briggs & Stratton, the Simplify 6.6. That's a 20 kilowatt hour stack there. There are some really nice features of this battery. One is just how quickly it installs. Two is it's a very high power battery. So there are power limitations, output limitations on batteries. Each of these modules is capable of 1C continuous output. That means for each of those modules, 6.6 kilowatt hours. The controller does provide some limitations overall on that, but this battery is capable of 14 kilowatts of output from a single stack. You can do up to 6 of these stacks in parallel. Also get a high number of cycles out of this. This is superior chemistry. This is LFP chemistry, which Briggs & Stratton with the Simplify line has been producing for 15 years. I know the industry has all moved towards LFP chemistry because of the superior safety and the larger number of overall cycles.
Now, Nathan, I just want to let everyone know we have about 7 minutes left. So if you have any questions, please put them in the Q&A. We'll let you know. Nathan, go back one slide.
Sure.
I know we're kind of running up on time, but when we did lead acid batteries, it was always we shouldn't do more than 80% depth of discharge or 50% depth of discharge. It makes the battery last longer. But what we're showing here is 100% depth of discharge, and but it's the charge rate that's changing this amount of cycle life. Can you just speak a little bit to, why are we still allowing 100%? But it's not the depth of discharge on these lithium-ion batteries, but maybe the charge rate.
Well, there are a couple of things. Certainly, depth of discharge does play a role in the lifetime of your batteries, right? We're seeing the greatest amount of lifetime with LFP batteries when you reserve about 20% overall capacity. But the rate of charge and discharge also plays a role because the rate of charge and discharge influences the creation of heat inside the battery. So, a battery run at very high speeds. I mean, we're talking about a 0.5 C charge rate means charging that battery up in 2 hours or discharging it in 2 hours. A 0.75 means an hour and 20 minutes, right? Most customers are not going to discharge their battery that quickly, right? If they do, they probably have a battery that's not really sized to back up their home for very long. Most customers want 15 hours of backup, 20 hours of backup, and typically they're getting that with 1 or 2 stacks of batteries. So these are lab numbers, right? Showing how, what the expected life cycle of the battery is based on a laboratory charge and discharge cycle occurring rapidly. But I mean, to answer your question, why charge rate plays a role as it influences the temperature at which the battery is running. When you're running at extremely elevated temperatures, that does result in the electrolyte not lasting quite as long. So great questions. I point out this is mostly a residential battery for us. We can do up to 120 kilowatt hours of storage. That's a long amount of time. It's a large amount of energy to have for your home. And that can do up to 84 kilowatts of continuous power output. Most of our customers are doing 1, 2 stacks. We've seen some bigger systems with 4 stacks of batteries as well. Off-grid systems, typically require a little bit more storage since they don't have that utility to rely on. Daniel, we have other batteries as well. We even make a 24-volt battery, right?
Yeah, which is uncommon, I think, in this industry. A lot of people are moving 48. We even have a
Why
12
might you
volt
want
option.
one? Why might you want a 24-volt one?
Well, if you got all that great old Victron equipment, or maybe new Victron equipment that you don't want to necessarily replace because you still have existing 24-volt lead acid batteries you might be replacing.
Exactly, right. So if you're looking to do a retrofit, I mean, we were talking about AC and DC coupled systems here. You might want to still have a 24-volt option. We do make the PHI battery in 24 volts. The Amplify battery there, the second one in, that's made in Oxnard, California. So is the PHI battery on the left. That Amplify battery carries a 15-year warranty, so really long warranty on that. We also, if you're interested in commercial projects, have a whole line of high voltage batteries. These can go up to 1200 volts. And this is for our commercial and projects. So here's an example of that on the screen. So if you do have a commercial battery project where you're looking at doing high voltage batteries, we have options and we have a team that can assist you. So if you have some questions on that, feel free to reach out to Daniel and I. You will be getting a follow-up email with all of these slides. And Daniel, just quickly, let's show the My Solarc app here. You do have the ability to remotely monitor your system or your systems. So showing here an example on the screen where you can see all of the systems that you've installed. If there are any notifications, the Solarc app can let you know about those.
I would also argue one of the nicest features is the ability to not only monitor, but also change settings.
Yep.
Perhaps you forgot to change a setting, you can remotely get in there and change it for the homeowner without having to do a truck roll.
And even our team can do that for you, right? So you can share your Solarc plants with us. And if you're working on a plant and you need some help, you can share the configurations with us and we can help you configure remotely. Additionally, you get to monitor the batteries. And because our batteries have closed loop communications with the Solarcs, you can see a lot of battery information just through that Solarc app itself. You can look at charge and discharge. Hey, as a physicist, Daniel, I like to point out there's a little bit of a difference between the charge and discharge amount on all of these days. Why is that, Daniel?
Temperature?
Nope, there's inefficiency, right? So you're always going to use a little bit more energy charging than you're going to get out on the discharge, right? And so, we mentioned before about 5% of the energy with a DC coupled system, is lost due to inefficiency. With an AC coupled system, you're looking at a little more, about 15%. And of course, those do depend on charge rates, etc. Daniel, I know we're at the end of the hour. We have this great offer out to those that join our IQ installer program. If somebody wants to join it, what do they get and who should they contact?
They can contact me, email. The email is going to pop up here in a second. They can also scan this QR code. Go ahead and enter if you're installing our batteries. We'd love to have you. If you haven't installed our batteries yet, we're going to give you $1,000 off your first install. Nathan, let's go ahead and pull up the email. So if you're looking for your NABCEP credits, please email energy storage training at BASCO, B-A-S-C-O, Briggs and Stratton Company.com. Email us your full last name. Also, email us if you're going to be at NABCEP. I'll make sure that we have one of our Lego kits available for you. We did get one question, and if anybody hasn't put in a question that they want answered, please put that in now. Mark is asking, what is it that limits the number of batteries in a system? And I like that question because he didn't say what is the number limit, but what is it that limits the number of batteries in a system? And maybe we can be specific to our batteries or other batteries.
Well, I'll start off by telling him why we're limited to the number of modules that we are with 6 stacks, right? So we are limited to 18 modules in our systems based on communication. There's a lot of communication that's happening from battery modules to battery controllers to each other, and then those aggregated controllers into the inverter. So the coding for our batteries, we limited it to 16 battery modules. That could be expanded in the future. It's not related to the power flow, right? So if you were operating an open loop, with our PHI batteries, our Amplify batteries, we can put huge numbers of batteries in parallel, right? But there's also the consideration of keeping all those batteries balanced. And so that is important as well, to make sure that the cable lengths are the same, that the systems are as symmetric as possible, to make sure that each of the batteries is doing their appropriate amount of work. So for us, the limitation on 16 batteries is purely a communications, and it's a product decision, right? Overall, we decided to limit based on comms to 16 batteries because, or 18 batteries, I'm sorry, 6 stacks of 3. But yeah, good question. Are there others, Daniel?
No, there's not. I just want to thank everyone. Thank you, Nathan. I think AC coupling, although as we mentioned, isn't as efficient, there's a lot of opportunities. There's a lot of AC coupled systems out there. People are looking for the backup. There's probably also a lot of AC coupled systems out there that are going to be losing their NEM status as they get grandfathered out. That is going to see the need for us to add battery energy storage to a lot of these systems. Thank you. Please come visit us at NABCEP. I love it. And Nathan, any final thoughts from you?
I guess one thought that came to mind is one other limitation on battery system sizes is code. So Daniel, you do a nice talk on codes and standards, and most locations you're limited to 80 kilowatt hours. So your garage, the outside of your house, you can have 80 kilowatt hours maximum there, in stacks of 20. So regulations also influence the size of battery systems, although hopefully those are going up as safety improves, right? As safety systems get better and better, hopefully we'll see some increases in the amount of capacity that you're allowed to install.
And the testing to show they are safe as well.
Yes, and that's something that's been a focus of the Simplify brand for a long time, is safe, effective systems. So Daniel, everyone, thank you for your time this morning. One of the things that we certainly love to do is help out. So if you've got a complex project, maybe it involves generators, AC coupling, etc., go ahead and reach out to us. You will be getting this slide deck and a recording in an email that follows up this talk. So thank you, everyone. Have a wonderful day. Bye.